date 29th of November, and today we have studied about heat exchanger. And heat exchanger, first thing that we will start off with that area density. So area density basically means that surface area of the heat transfer by the surface area volume. So density is mass by volume, so that is surface area mass upon volume by volume. So by volume, what do you actually do? We actually just try to figure out the how compact or how big is the, so that from the ratio, like for beta 1000 it's for cars it is for 1000, and for gas turbine it's almost like 6000, and refrigerant also it has been given simple thing. And beta value, when it is less than 700 meter cube per meter square per meter cube, then heat exchanger is said to be compact, and after it is big. So now there is a two type of heat exchanger, that is sorry four type. That is parallel flow, it is very simple. Counter flow, one side it is going this side and it is going opposite side. Then cross flow, so it is going horizontally where it is going vertically. And multiphase, multiphase means there is too many pipes, they are going, the fluid transfer is happening simultaneously. So all these four types we are just going to read. Also there is double pipe heat exchanger, like there is two pipe and hot fluid will pass from one pipe and cold fluid pass from another pipe. And parallel flow, both counter flow process, same thing it has been written here. Now we are just going to see that overall heat transfer coefficient, that is divided by mu. We have been seeing it. So mu or in what you can say mu. So here it is HA, it has got T infinity I outside temperature, HO, and HI means inner, HO means outer. And then where it is getting convection on side, there is on conduction and also convection, those three things that are happening. So convection 1 by HIAI, conduction, that is ln R2 max 1. So you know, for dirty surface there is one phenomena that is called fouling resistance, and fouling resistance has been found out from scientific way, like from trial and error. There is no certain value that can be found. So fouling experience, that can say, like in a simple smooth pipe, what can happen over time, there will be some clog formation or something, for the pipe will not want to be smooth, and in that case there will be fouling resistance. So that's some. And then so here you can see pi equal to total temperature by total resistance, that is mu into A into AT. That is external law of cooling. So external law of cooling, and then Newton law of cooling, that is here we are using. So mu has a sign overall heat transfer coefficient, that is written here. And then when outer and overall is same, then we can see ui ai 80, so u0 is 80, it is something like this way. So mu ai equal to mu as the temperatures are same. So mu inner surface, mu outer surface always specified. But for BTEC, the mu y we are taking average. We are just taking average. That is the same. Fouling resistance, how we can figure out from the old surface and differentiate from old surface and new surface, then we can count the fouling resistance. And the unit would be watt per meter square Kelvin or watt per meter square second. And U can be also Q by A into delta T, that is overall, as H equal to Q by A into delta T. From here we are getting this. So fouling, that's one. So for new pipe we are getting UII equal to 1 by the equation, that is for convection, conduction and convection again. And then it's we are getting similarly for outer surface also same thing we will get, and by as AI and AO are almost similar, then we are just comparing, and we'll just gonna get UIRA equal to URO. And for plane surface what we are saying, UI equal to UO. But here is RA square, that is also coming RO square, because the radius of the inner surface and outer surfaces, they are different. But for plane wall, the difference on the length, that is almost same. So that's why we are just eliminating those two things. Now generalized law of thermal energy balance. So the notation first will come that MC mass flow, and for hot MC, so blah blah blah, we know that. Now for the first thing that will happen, what is happening, this here we are taking two from one pipe, it is hot fluid, from one that is cold fluid, that is going. Now steady flow energy equation, that is h1 plus v1 square by 2g plus z plus q equal to h2 to v2 square by 2z plus z2 square. And that the equation, just remember what was the equation. h1 plus b1 square by 2 plus z1g plus q equal to h2 into v2 square by z plus z2z plus w. That is, there was q is the heat input and w was the work output that was been given as far as I remember. So q equal to h2 minus a1, that is the heat transfer, q the heat transfer rate m dot, so m dot c p dot, and from there we are just manipulating all these things, and what will be getting, this is the final equation that you is equal to m dot h is th minus tc, or m dot cc tc minus tc1. So tc minus tc1, tch1 minus tch2. So for hot fluid 1 tch1, and cold fluid that is tch2, something would be there. So where, so like this tc2, let me write down, this is tc2, they have just missed it, this is tc2 minus tc1. Okay, now transfer to heat transfer capacity, simply divided by c. C must go right into specific heat. The unit would be joule per second Kelvin or watt per Kelvin, and it is how much the energy is required to change the temperature of the body by 1 degree Celsius. It is how much the energy that will be required to change the body temperature by 1 degree Celsius. And then, so fluid undergoes last temperature variation under given fluid having heat transfer capacity. So what has been given here? Fluid undergoes last temperature variation at a given time for having minimum heat capacity rate. Okay, so when minimum heat transfer rate will be given, that time that particular fluid will easily gonna transform, and when the rate is more, it will take more time. Like for a, suppose for water it is 4.187, some fluid like for mercury it is 13.87, then it will just gonna take more time. And heat capacity ratio, that is R is C minimum by C maximum, and when both are equal heat, then C minimum by C maximum, and when it is for phase change, then the C minimum will also be 0. And so C minimum, what was that? That is heat capacity rate, and C maximum, that is also heat capacity. So basically it is given for sensible heating, not for latent heating. Now logarithmic mean what has been given here. So first the assumptions: one dimensional steady flow. Steady flow means du. So what has been given was dt by d is bigger t, so that was d bigger t by dt was 0. So what was being given, dt means temperature gradient. Temperature gradient with respect to time, temperature gradient with respect to time for a steady flow energy, that will be 0. That is been simply said by dt equal to 0. So there is a equation of qg by k plus equal to dt by dt. That case also that was the same. So no internal heat generation, simple. Neglect the kinetic potential energy, all thermophysical properties. Overall heat transfer coefficient was 0, I guess. I haven't tried it. Outer surface is heat exchanger. Radiation is method. I will see once see again, then I will confirm. So from here, what is happening? See at the chart. It is a theoretical chart. Okay. So what is happening? From upper side in a pipe, there is a hot fluid flow. From the lower side, that is a cold fluid flow. So what will happen? Hot fluid temperature will go down and cold fluid temperature will go up. So that's why in the rate, the hot fluid, the temperature is going down, and at last that is th2, it is lower than th1. But for the for the cold fluid case, what is happening? At first the temperature was very low, that was tc1, and then it is getting gradually greater, and after gaining some heat, its temperature get higher and goes to dt2. So DTC is that the temperature change for cold fluid, and DT is the temperature change for hot fluid. And DT delta T, I guess it is at first when it was starting, what is the temperature gradient difference, and DT at last. So why negative is coming, you may ask, because DTH here, the for hot fluid, it was being final minus initial. For final case, it was getting less than the initial. Like for suppose hot fluid was 100 degree, at last it was at, sorry, I am giving the example, yeah, right, 100. So here 80. So what would be happen? The final one is the initial, that is be negative. So that's why we are taking negative at first before that. But in second case, it is temperature is gaining, so last will be greater than the first. Simple. Then manipulation dq water, and then dt equal to up because we are taking it as up. Okay. Now this equation will come. Then we are just differentiating from delta t1 to delta t2. So delta t1 to delta 2 because from this gradient is going on now. So from the boundary condition we will just gonna get that and differentiating. So that is delta t2 minus delta t equal to q into mu cp. Okay, from there mu is getting is simply this equation, and at first you will go up, and from there what is been given dq equal to m dot cp is that is mu pa into delta t. That's what has been put in here. Then we're just taking it in this side, so mu p. So from sorry mistakenly written. So from here mu p is getting, from here mu p is getting here. Okay, delta t to delta 2 0 to delta. Okay, we're just differentiating this equation. So what I have written here is that it will just want to take use in later part. From there ln part we are just getting ln part, but then what we are doing, so you must from here it is getting, so it is getting from mu p value this thing value is putting here. Then q, we are just shuffling the terms and q is getting here. So then delta t average, this whole is taking as delta t average. So delta t average is also called as lmtd, that is delta t1 minus delta 2 by ln delta t1 by t2. Also we can write is delta t2 minus delta t1 by ln first t2, that was ln t2 by ln t1. That is in both ways we can write it, remember it. And from here what we can see, it is delta th2 minus t1 and th2 equal to mu equal to lmtd, that has been written here. From here lmtd we are getting this thing. So and at last, so about the signs of lmtd. So from these two equations, from here also we are getting, from here also we are getting what is lmtd. What this equation sign means, so for the first case, that is delta t1 value is greater than delta t2. So what will happen, delta t1 value is greater than delta t2, so it will be positive. Simple, no problem there. But when what happens when delta t2 value is greater than delta t1, so delta 2 value is greater, so it will negative will come. So what I guess ln negative will come, we'll just gonna reshuffle it, take the minus outside, and then also in negative also it will come negative, and negative positive. So identity is always positive, and parallel flow case delta t1 equal to delta th, delta 2 equal to ch. Okay, in parallel flow delta t1 value we are getting th minus c1 t. So what I have gotten in this equation, so lmtd in degree Celsius or Kelvin, that is doesn't matter. So just for once confirm when delta 2 value greater than, so what we delta 2 we are just taking the denominator into the numerator and then just doing a double pipe heat exchanger. So what is happening, hot fluid this side, like cross flow, cold fluid on the opposite side. So what will happen, so what will happen, give me a good example for it. So like you are taking something and someone is taking it from you, so what will happen, your energy will go down and his energy also gonna get down, but your energy. So what is happening here, just say, so first the fluid temperature is getting lower, but as the lower fluid is getting in the opposite direction, so first the temperature would be low, but then in the later stage at final the temperature would be low, but at initial the temperature would be high. Sorry, what is I'm doing, just simply first thing higher to lower, but second thing what is happening, from lower to higher it is going, from lower to higher it is going, but direction is this. So that's why when delta th, that is final minus initial, and the final temperature was less. That's why for those two cases we are taking negative. Same equation, same manipulation, and then last part. So what is last part? The relation between LMTT and EMTD we are just stating. So from here we are getting EMTD hello, LMTD hello first we've discovered. And then what is doing? We are just manipulating delta T1, delta T2, that was the same, but for ln part we are just assuming it 1 plus this thing by 1 plus. If you just do it by hand, I will try. So what will come? Delta T1 plus delta T2 minus delta T1 minus delta T2. So delta T1 from here to, if it come here, delta T1, delta T2, those will just gonna get cancelled out. Okay, if both things will cancel out, and we'll just gonna leave to it ln delta T1 by delta. Same thing will come, x value we are taking as this, then ln P equal to T2 minus T1 by ln x 1 plus x by 1 minus x. Then here is getting, it is the Fourier series expansion we are doing. I think Fourier series that was there. Simply not remember like Fourier series, and for higher order as it is negative, as the x value is negative, why x value is negative, that say 1 minus x by 1 plus x. Here not was, it was not, yeah, x value is less than 1, less than was because at the denominator it is positive. So always the addition of positive is greater than the multiplication, subtraction of 2 things. So that's why negative will come. 1 minus this thing, negative will come. And what x will be less than 1. So that's why just taking the higher orders. So 2x by 2x by 2. Another way we can get the same thing is that, so LMTD value, this thing, then what is getting? We're just putting the x value here and square, then this thing same, then we are getting the LMTD value from here. LMTD and EMTD relation we are getting from delta 1 plus this, because this thing is counts as EMTD. When T2 is greater than T1, so when delta T1 is greater to T2, so when delta T2, T1 is greater than T2, so what will happen? There will be some value that will come here. Yeah, some value will come here, but it is negative. It will be negative, so that's why the entity value will come negative. But when delta T1 is less, then negative value will come. So what is happening? Just simply say, when delta T1 value is greater, it will be less than 1, but it will be positive. Okay, it will be positive thing, so that's why it will be greater. But when negative value will come, what will happen? Delta T2 is greater here, so negative value will come. So here also delta T2, so it will be less, so LMTD will be less, AMTD will be higher in that case. In that case AMTD will be higher, and in that case LMTD. So some confusion is there. Just to get the thing in later part and try to figure out. And both are equal. In one only case both are equal, that is in this case. There is one simple case though, where LMTD and EMTD counterflow. For counterflow heat exchanger, only it is the only one case where LMTD and EMTD are equal. Also here one more thing that I need to consider, heat transfer coefficient somewhere. Yeah, independent MTD, yeah, L hospital rule. So here L hospital rule has been put. So what is this basically doing is L hospital rule. So basically when something you are putting in a limit, it is indeterminate form, instead of doing some calculation, what we'll do, we'll differentiate the denominator and numerator. So we're differentiating it both. What value is coming, we are seeing, then we are putting the limit value. So that's why simply we are getting this value. So limit value, if you put x equal to x tends to 1, so what will be, it will tend to 1, then delta to 1. So legal hospital, basically we are just doing, we're just getting the value in a simply in a less limited time. So basically when there is a indeterminate form, we are just going to differentiate the denominator and numerator simultaneously and then put the limit value, and then LMPT value is there. So counter flow, basically this heading. So one more thing that I am not clear, just let me see. So here also area is not same, that also is like parallel and counter because. So also for a find cross flow connection, cross flow or multi-related, F is calculated in a graph. What is F? It is concentration factor.